Let us continue our discussions on S parameters. We look into the properties of 3-port network. So, using the properties of S parameters, we show that a 3-port network cannot be lossless, reciprocal and matched at all 3 ports. That means, we cannot have a 3-port which is lossless, which is reciprocal and it is matched at all 3 ports. So, let us see how we can demonstrate this. In order to prove this, we start with the assumption that it is possible to have a 3-port network which is lossless, reciprocal and matched at all 3 ports, and then we will show that such assumption will essentially lead to contradiction. So, a 3-port S parameter can be written in this form: S11, S12, S13, S21, S22, S23, S31, S32, S33. Now, if we consider that all the ports are matched, then we get an S parameter where the diagonal elements are 0. S11 is 0, S22 is 0, S33 is 0. Now, next, if we consider it to be reciprocal, then the S matrix is symmetric. So, we will have S21 equal to S12, S31 will become S13, similarly S32 will become S23. So, this is the form of S matrix when it is assumed that it is matched at all 3 ports and also it is reciprocal. Now, let us bring in the other issue, that means losslessness of this of the network represented by such S matrix. So, we know that if we apply the properties of S parameters for a lossless junction, we can write S13 into S23 is equal to 0. This comes from S13 into S23 conjugate is equal to 0. Now, to satisfy this, either S13 has to be 0 or S23 conjugate is 0 or both has to be equal to 0. So, let us assume that S13 is not equal to 0, then S23 will be equal to 0. The lossless S matrix will also satisfy the unity property, and considering our network, we find that we will have mod of S12 square plus mod of S13 square equal to 1, like that for all the columns. So, if we consider this type of relations, we can write mod of S12 square is equal to 1 minus mod of S13 square, and it can be made equal to 1 minus mod of S23 square. Now, if the above equation is to be satisfied, then we must have S13 equal to S23, and this will lead to S13 equal to 0, because we have earlier said that S23 is equal to 0, but S13 equal to 0 contradicts our earlier assumption that S13 not equal to 0. Therefore, we cannot obtain a consistent solution with the given form of S matrix, and therefore, this S matrix, which is reciprocal matched at all 3 ports, cannot be lossless, and we make this statement: a 3-port network which is lossless, reciprocal at the same time, matched at all 3 ports we cannot have a solution for the S matrix. What we can do? We can drop the condition that S is reciprocal. So, once we drop this condition that S is reciprocal, then we get this form of S matrix, and this, if it is lossless, that means this S matrix is representing a lossless junction, then by the properties of S matrix we will have S31 conjugate S23 equal to 0, S12 conjugate S13 equal to 0, S23 conjugate S21 equal to 0. And also if we look at the individual columns, magnitude of S21 square plus magnitude of S31 square equal to 1, and similarly for the other two columns. Now, this set of conditions can be satisfied if we consider S12, S23, S31 equal to 0 and S21 mod of S21 is equal to mod of S32 equal to mod of S13 is equal to 1. You can see that if we put S12 equal to 0, then mod S32 becomes 1. Similarly, if we put S23 equal to 0, then mod S13 becomes equal to 1. Like that we can verify that we have a solution of this equation provided these relations are satisfied. That means S12, S23, S31 is 0, then we get a solution for the remaining parameters S21, S32, S13. In the same manner, another set of solution is possible. Instead of this being 1, either this S21 will become 0, S32 will become 0, S13 will become 0. Then we will find S31, S32, S12 all will have unit magnitude. Now, these two sets of solution give rise to a device which is non-reciprocal and it is called a circulator. So, what we can do, these parameters magnitude is unity, and by proper choice of the reference plane their phase can be set equal to 0. So, S21, S32, S13 becomes equal to 1, and therefore, we get this matrix. Here this matrix S essentially represents a circulator which is shown here. So, when you excite port 1, it goes to port 2, not to port 3, and you can see that S21 is 1. Similarly, when a signal is incident at port 2, then it goes to port 3, not to port 1, and therefore, we have S32 is equal to 1, and finally, when the signal is incident at port 3, it goes to 1. So, S13 is 1. Please note that from one port to another it rotates in the clockwise manner. So, it is a clockwise circulation. If we consider the 3 ports satisfying the condition S13, S32, S21 0 and S31, S23 and S12 is equal to 1, then this will give rise to, by proper choice of phase references, we can get a S matrix of this form, and this gives rise to again another circulator, but this time the sense of rotation or the circulation is counterclockwise. That means, when we have port 3 excited, then we have the signal going to port 2, not to port 1. So, we have S 2 3 equal to 1, and next S 1 2 equal to 1. So, from 2 it goes to 1, and finally, from 1 to 3. So, it is S 3 1. This circulation is in the counterclockwise sense. Later on we will see, when we discuss some of the microwave practical systems, this type of circulators find lot of use in radar system. We move on to another topic, which is the change of reference plane. We have already seen that when we consider a n-port microwave network and find out the S parameters, the phase reference is defined at the terminal planes. For example, Z1 is equal to 0 will be with respect to this terminal plane. Similarly, for the nth port, if we take capital Nth port, Zn equal to 0 will be here. Now, many a time, for example, the evaluation of S parameters or measurement of S parameters not possible to be done at the reference plane where we want the S parameters. So, what we can do? We can modify the S parameters, original S parameters measured for this n port network, considering this as the reference planes, by change of reference planes, and let the reference plane be now moved to Z1 is equal to L1 and Zn equal to Ln. So, it has been moved by this distance, and then modified S parameter S dash becomes S pre and post multiplied by these two matrices, where the off diagonal elements are 0 and diagonal elements e to the power minus j beta n ln. So, for the port 1 it is e to the power minus j theta 1, which is equal to e to the power minus j beta 1 L 1. Like that, all diagonal elements will give the phase shift that is resulted due to the movement of the reference plane. And it may be noted that the S matrix is pre and post multiplied by such matrices to get the equivalent S parameter matrix S dash. So, we have discussed the various aspects of S parameters. Next, we will discuss another set of parameters which are known as transmission parameters or ABCD parameters. We have seen that we can use different types of parameters such as Z, Y, S for representation of microwave networks. We have also seen that S parameters are very popular in representation of such microwave networks, because they can be measured directly. Now, we introduce another set of parameters which are called ABCD parameters or transmission parameters. These parameters, as we will see, will be particularly useful when we deal with cascaded systems. So, for a 2-port network, the ABCD parameters are defined as, for this 2-port network, we have V 1 and I 1 in the port 1 related to V 2 I 2 of port 2 by this matrix relation. V 1 I 1 is A B C D V 2 I 2. Now, for example, we can calculate the parameter A as V 1 by V 2 when I 2 is equal to 0. That means, when the port 2 is open circuited, at that time the ratio of voltage in port 1 and port 2, this will give the parameter A. In the same manner, we can find the other parameters B, C and D. For example, B will be V 1 by I 2 when V 2 equal to 0. Now, as I told that these parameters are particularly useful when we have a cascade of 2 ports, and in practical microwave circuits we will have different subsystems represented as 2 ports and they are cascaded. So, when we have this type of a cascade of 2 ports, 2 or more, here we are showing 2, we can write the overall ABCD matrix as product of ABCD matrices of individual 2 port. So, this entire cascade can be represented as a single 2 port, and the voltages and currents at port 1 and port 2 will be related, and this resultant ABCD parameters can be found as product of the ABCD matrices of the individual 2 ports. Now, let us see how we can evaluate these ABCD parameters for some simple 2 port network. Here we consider a very simple 2 port network where we have a single series element Z. So, this Z is a impedance element, and if we find the ABCD parameters for this type of simple 2 port, we find that when I 2 will be 0, in that case I 1 also will be 0, because now a open circuit will be created here, and essentially V 2 will be equal to V 1. So, for this type of a 2 port, we will have A equal to V 1 by V 2, I 2 equal to 0, this will become 1. And since I 1 has become 0, C, which is I 1 by V 2 under the condition of I 2 equal to 0, this becomes 0. Next, when we put V 2 equal to 0, that means we short circuit here, then I 1 becomes equal to I 2, and therefore, we can find B, which is equal to V 1 by I 2 under the condition V 2 equal to 0, it can be written as V 1 by I 1 and which becomes equal to Z, and D which is I 1 by I 2 for V 2 equal to 0, it becomes I 1 by I 1 and it becomes 1. So, for this 2 port or this series impedance element Z, we can write the ABCD matrix as 1 Z 0 1. Let us now consider another example where we consider a section of a lossless transmission line which is having characteristic impedance Z naught and phase constant beta. The length of this line is L and this is considered as port 1 and this is as port 2. So, we want to find out the ABCD matrix for these 2 port. Now, for a transmission line, in general we can write V Z is equal to V plus e to the power minus j beta z plus V minus e to the power j beta z, and I z is 1 by z naught V plus e to the power minus j beta z minus V minus e to the power j beta z. So, this voltage and current expressions are valid when we have wave travelling in both plus z and minus z directions. Now, we set the reference say z is equal to 0 at port 2. Therefore, at port 2 V 2 becomes V plus V minus and I 2 becomes 1 by z naught V plus minus V minus. Now, let us see the definition of A. A is V 1 by V 2 when I 2 equal to 0. So, in order to find out the parameter A, we need to calculate V 1 here at port 1 and also find out V 2 under the condition I 2 equal to 0. So, when I 2 equal to 0, V plus becomes V minus and therefore, we have V 2 equal to 2 V plus and V 1 we can calculate by replacing this Z by minus L. So, V 1 becomes equal to V plus e to the power j beta L plus, now we can write V plus here and therefore, e to the power minus j beta L. And now, if we take out this V plus and divide by V 2 which is 2 V plus, we will get e to the power j beta L plus e to the power minus j beta L by 2 and therefore, A becomes cos beta L. Now, let us see the parameter C which can be found for the same condition when we have I 2 equal to 0 and C is I 1 by V 2 when I 2 equal to 0. Now, I 1 can be written as 1 by z naught V plus e to the power j beta L, z has been replaced by minus L minus V minus has been replaced by V plus e to the power j beta L. And therefore, now we can write one by 2 z naught e to the power j beta L minus e to the power minus j beta L, because this V plus when taken out will cancel with the V plus of V 2, and this can be written as j y naught sin beta l, where y naught is 1 by z naught. In the same manner, we can show that B is equal to z naught sin beta l and D is equal to cos beta l. And therefore, we have ABCD parameter for a section of transmission line is given by cos beta l, j z naught sin beta l, j y naught sin beta l and cos beta l. Let us now consider some more examples. We have considered a two port in the form of a series impedance. Let us now consider a two port of the form of shunt admittance y, and for this case the ABCD parameters can be found out to be equal to 1 0 y 1. Similarly, if we have a transformer in the circuit with turns ratio n is to 1, for this we can find the ABCD parameters to be n 0 0 1 by n. So, this can be derived once again considering the fundamental relation between the port voltages and currents with the ABCD parameters. Now, let us see how we can relate the ABCD parameters with S parameters. In fact, later on we will see that in some of the cases where the direct computation of S parameters may be difficult, we can actually find out the ABCD parameter first and then we calculate the S parameters. So, for that we need to establish the relation between S parameters and ABCD parameters. So, let us consider a two port once again, and let us assume that both the port impedances are same equal to Z naught. So, under this condition, when the port impedances are same, S11 equal to V 1 minus by V 1 plus, when V 2 plus is equal to 0. So, let us see how we can express these voltages V 1, I 1, V 2, I 2 in terms of V 1 plus, V 1 minus and Z naught. So, we can write V 1 to be equal to V 1 plus V 1 minus and I 1 to be equal to 1 by Z naught, V 1 plus minus V 1 minus. Similarly, V 2 is V 2 plus V 2 minus, but note that this current I 2 here, it is a outgoing current, and that is why we write minus I 2 equal to 1 by Z V 2 plus minus V 2 minus. And we have V 1 from this two port is equal to A V 2 plus B I 2. So, when V 2 plus equal to 0, we have V 2 is V 2 minus and I 2 will become V 2 minus divided by Z naught. Now, I 1 is C V 2 plus D I 2, and this can be written as, in place of V 2 we write V 2 minus, in place of I 2 we have seen I 2 becomes V 2 minus by Z naught. So, we write V 2 minus by Z naught. So, we can write I 1 to be equal to C plus D by Z naught V 2 minus. And we have V 1 to be equal to A V 2 plus B I 2, and therefore, we can write V 1 plus V 1 minus. In the same manner, we substitute V 2 is equal to V 2 minus, I 2 equal to V 2 minus by Z naught, and we get A plus B by Z naught V 2 minus. Now, if we express V 2 minus as I 1 by C plus D by Z naught, then we can write V 1 plus V 1 minus is equal to A plus B by Z naught into I 1 divided by C plus D by Z naught. Now, we can substitute I 1 as 1 by Z naught V 1 plus minus V 1 minus, and this can be written in this form: A plus B by Z naught, C Z naught plus D, and this Z naught will get cancelled, into V 1 plus minus V 1 minus. So, once we have this expression, now we can rearrange. We can take all V 1 plus terms to the right hand side and V 1 minus terms to the left hand side. So, if we rearrange these terms, we can write S 1 1, which is V 1 minus divided by V 1 plus. It can be written as A plus B by Z naught by C Z naught plus D minus 1. So, this divided by A plus B by Z naught C Z naught plus D plus 1. Here you can see that when you take V 1 minus term this side, you get 1 plus A plus B by Z naught divided by C Z naught plus D, and once you take V plus this side, you get A plus B by Z naught C Z naught plus D minus 1, and from that we can find V 1 minus by V 1 plus, and then you can put it in this form: S 1 1 equal to A plus B by Z naught minus C Z naught minus D divided by A plus B by Z naught plus C Z naught plus D. So, we have actually related S 1 1 to A, B, C, D parameters, and Z naught is the normalizing impedance. We can carry out similar exercise for all the 4 S parameters, and they may be related to ABCD parameters as S 1 1 we have already seen. S 1 2 is 2 A D minus B C divided by A plus B by Z naught plus C Z naught plus D. Similarly, S 2 1 is 2 divided by A plus B by Z naught C Z naught plus D, and S22 is minus A plus B by Z naught minus C Z naught plus D divided by A B by Z naught plus C Z naught plus D. So, once we have these relationships established, if we know the ABCD parameter for a 2 port, we can find out the S parameters, and this gives us the ease of calculating the S parameters, particularly when we have the 2 ports in cascades. We can find out the ABCD parameter for the individual 2 ports, and then we can combine these ABCD parameters to get the equivalent ABCD parameter for the whole cascade, and then we can find out the S parameters directly in terms of ABCD parameters. Later on we will see such examples where we will have to calculate S parameters by first calculating ABCD parameters. So, in summary, in this module we have seen the representation of n-port microwave networks. We have introduced the different types of parameters Z, Y, S, which are used to describe such n-port network. We have seen how these parameters can be evaluated for some simple networks, and finally, we have introduced the transmission parameters or ABCD parameters, which are very helpful in finding out the S parameters for cascaded systems. So, in the next module we will discuss different ways of doing impedance matching in microwave circuits.